Welcome to the deep dive. Okay, just take a second, look around outside. You probably see them everywhere, right? Utility poles, lines, crisscrossing overhead. They're so, I don't know, there that we barely even notice them most of the time. But what if I told you there's this incredibly complex world hidden in plain sight? Engineering, physics, really detailed rules. It's way more than just wood and wire. It's like this invisible system keeping everything running, lights, internet, all of it. And crucially, keeping us safe. So today we're going to pull back the curtain on that. We're diving into a document called CPUC Strength Requirements.pdf. It's from the California Public Utilities Commission, and it basically lays out in really fine detail how strong utility lines need to be in California. Our goal here is to unpack just how much thought, how much precision goes into making sure this stuff doesn't fail. So where does a document like this even start? How do you define strength for something like a utility pole?
Well, it really begins with this fundamental idea of public safety. That's the bedrock. What's so fascinating, I think, about this document is that it's not just about, brute force or raw strength. It really lays out a very systematic way of thinking about hazards, identifying them, minimizing them to maximize safety for everyone. It's a philosophy woven into the rules themselves.
Right, that focus on safety makes sense. So, okay, how does it start categorizing risk? What's the first step in figuring out how strong something needs to be?
They start by classifying the lines, breaking them down into different classes of circuits. So you've got things like class E, H, and L. Those are different types of power supply lines, different voltages. And then class C, that's for communications, like your phone lines or fiber optics. And the key thing is the class of that circuit and how close it is to other lines or maybe buildings or roads. That interaction determines what they call the grade of construction.
Ah, okay. Grades of construction. So that's
Right.
like a safety rating.
Pretty much, yeah. There's a hierarchy. You have grade A, grade B, and grade C. Grade A is the top tier, the most stringent requirements.
Gotcha. So if a line is just out on its own, not crossing anything, not sharing a pole.
Then it's usually simpler. Like those higher voltage class E or H lines, they generally need to be grade B. But the lower voltage class L power lines and the class C communication lines, they can often meet the grade C standard in those isolated situations.
Okay, that seems straightforward enough, but you mentioned interactions.
Right, and that's where it gets really interesting, and you see the safety logic kick in hard. When lines do cross each other or they run close together, what they call conflicts, or share the same poles, the requirements ramp up significantly.
Can you give an example?
Sure. Imagine you have a high voltage class E or H line way up high, and it crosses over class C communication line down below. Suddenly, that upper power line, it needs to meet grade A construction standards. Big jump.
Wow, okay. Just because it's crossing a communication line.
Exactly. Or think about railways. Any power line, E, H, or L, if it crosses a major railway track, always grade A, no question. Even crossing a minor railway track bumps an E, H, or L line up to grade B.
So the potential hazard, the risk to the public, if something failed right there, directly drives how strong it has to be built. It's a very direct link.
Precisely. And the system is designed to layer that safety. Rule 42.1, for instance, it says if you have multiple conditions that affect the grade, maybe it's near a railway and crossing another line, you must use the highest grade required by any of those conditions. You don't get to pick the easiest one.
Okay, that makes sense. Compounding safety.
Yeah, and it goes even further. Like if one line crosses, say, two other lines in the same span between poles, it has to be built as strong as if it were crossing the most demanding of those lower lines.
Oh.
Or, get this, if a line crosses another line and that second line is also involved in its own crossing somewhere else, the highest line has to match the grade of the line below it.
Whoa, okay. That's like a chain reaction of safety requirements.
It really is. It's designed to prevent any single point of added complexity from becoming a weak spot in the system.
All right, so once they've figured out this grade of construction based on all the risks and interactions, the next big thing has to be the environment, right? Wind, weather.
Absolutely. That's where Rule 43 comes in, temperature and loading. And loading here isn't just the weight pulling down. It explicitly includes vertical load, yes, but also transverse, that side-to-side forces, like wind and longitudinal forces, which act along the length of the wire itself.
Okay, and how do they account for that? California's got mountains, deserts, coasts, pretty different conditions.
Right, so they actually define two distinct loading districts based purely on elevation. First, there's the heavy loading district. This applies anywhere above 3,000 feet elevation. And here, they factor in wind, the weight of the wires, and ice accumulation.
Ice. How much ice are we talking?
They specify a radial thickness of half an inch of ice coating the conductors. And that ice, they calculate, weighs about 57 pounds per cubic foot.
Wow, that's a lot of extra weight.
It is. Plus, on top of the ice weight, they add wind pressure. 6 pounds per square foot on the iced-up wires, 10 pounds per square foot on flat surfaces like cross arms. And the temperature they assume for this maximum heavy load condition, 0 degrees Fahrenheit.
Brr. Okay, so that's heavy loading above 3,000 feet. What about below?
That's the light loading district, areas at or below 3,000 feet. Now here they consider wind pressure and the dead weight of the lines, but, and this is interesting, no ice loading is assumed.
No ice, but what about wind? Is it less?
Actually, no. The specified wind pressure in the light loading district is higher. It's 8 pounds per square foot on cylindrical surfaces, 13 pounds on flat surfaces.
Huh. Higher wind, but no ice. Why would that be?
It likely reflects typical weather patterns. Maybe lower elevations see stronger wind events without the same icing conditions as the mountains. Or maybe it's a way to ensure robustness even without the ice factor. The assumed temperature for max loading here is 25 degrees Fahrenheit. Still cold, but not freezing.
Okay, so heavy loading with ice and moderate wind. Light loading with no ice but higher wind. And you mentioned sag calculations.
Yeah, there's one consistent detail across both districts. For calculating how much the wires will sag, they assume a conductor temperature of at least 130 degrees Fahrenheit.
130 degrees, that's hot.
It is. It accounts for the wires heating up from electrical current and direct sun on a hot day, which makes them expand and sag more. So they design for both extreme cold with load and extreme heat causing sag.
Okay, they've considered the location risk, the weather risk. How do they translate that into actual material strength? How much stronger than the expected load does something need to be?
Now you're talking about safety factors. That's Rule 44. And it's a really crucial concept. Basically, a safety factor is the minimum required ratio between the actual strength of a material like its breaking point and the maximum load is designed to handle under those heavy or light loading conditions.
So if the safety factor is 2, it means the part has to be at least twice as strong as the maximum calculated load.
Exactly. It's the engineer's buffer zone, the built-in margin for error, for unknowns, for degradation over time. It's there to make sure things don't just break when they hit the theoretical maximum load.
And are these factors the same for everything?
No, they vary quite a bit. If you look at Table 4 in the document, it lays it out. Things like the conductors themselves, the insulator pins, the hardware, the guy wires, the messengers that support cables, those generally require a safety factor of 2 across all grades of construction, A, B, or C.
Okay, a factor of 2 seems common, but what about the poles?
Yeah, poles and towers are different, and it gets interesting there. A wood pole, for grade A construction, needs a safety factor of 4.
4. So it needs to be 4 times stronger than the expected max load.
That's right. But a metal pole for grade A only needs a safety factor of 1.5.
Whoa, why the huge difference? 4 versus 1.5.
It reflects the materials, right? Wood is natural, variable, it degrades differently. Metal is more uniform, its properties are better known, maybe its failure modes are more predictable. Reinforced concrete poles are interesting too. They need a factor of 4 for grade A, like wood, but only 3 for grades B and C.
Even foundations have different factors, you mentioned.
Yep. Foundations fighting against uplift like wind trying to pull the pole out need 1.5.
Oh.
But foundations resisting depression, pushing down into the ground, need 3 for grade A and 2 for grades B and C. It's incredibly specific.
And it's not just about when it's brand new, right? These factors matter over time.
Definitely. The rules cover the whole life cycle. Rule 44.1, installation and reconstruction, says new designs have to account for all the facilities planned for that pole eventually. And get this, they require keeping records of the load calculations for the entire service life of the structure. Decades, potentially.
Wow, that's serious record keeping. What about adding stuff later, like a new cable company wants to attach?
That's Rule 44.2, additional construction. Adding anything new cannot reduce the existing safety factors below certain thresholds. And for wood structures over 15 years old, you can't even do the calculation without performing an intrusive inspection, actually probing or testing the wood to see its current condition. You can't just rely on the original specs.
That makes sense. Wood changes over time. And when does something just need to be replaced entirely?
Rule 44.3 covers replacement. Generally, if the calculated safety factor drops below 2/3 of what was originally required for grades A or B, or below 1/2 for grade C, it's time for replacement.
Yeah.
But crucially, it also says the safety factor should never be less than 1, meaning even if it's degraded, it should still theoretically be able to handle the expected load, even with no safety margin left. Below 1 means it's overloaded.
So it's okay to operate with a reduced safety margin, but never below that bare minimum of 1.
Right. And there's one more piece here under safety factors that I think is really revealing about the practical side of this. Rule 44.4, cooperation.
Cooperation. Between who?
Between all the different companies that might share a single utility pole. The power company, the phone company, cable TV, fiber optic providers. This rule actually mandates that they share critical data with each other promptly, usually within 15 business days.
What kind of data?
Things like the latest pole test results, especially those intrusive inspection results. Information about exactly what equipment each company has on the pole, where it is, how much it weighs. Standard values they use for load calculations. It forces collaboration to make sure everyone's working with the same accurate information when figuring out if the pole can handle more load.
And if one company wants to attach something new and the pole owner says no,
The pole owner has to provide clear reasons why, backed up by calculations showing how the load limits would be exceeded. They can't just say no. It fosters transparency.
that's actually quite remarkable. Mandated data sharing for safety.
Okay, so we have the grades, the weather loads, the safety factors. How does this all translate into the actual design? Like, how strong does the pole need to be sideways versus up and down? Exactly. The rules get specific about strength in different directions.
Yeah.
We're talking transverse, vertical, and longitudinal strength.
Okay, let's break those down. Transverse. That's sideways, right? Like wind.
Primarily, yes.
Yeah.
Rule 45 deals with transverse strength. It's mostly about horizontal forces, mainly wind pushing on the wires and the pole itself. There's a neat detail here. If a pole structure carries more than 10 wires, they only calculate the wind load on 2/3 of the total number of wires.
Why only 2/3?
It assumes some shielding, the wires in front block some wind from the wires behind them. It's a more realistic calculation than assuming full wind on every single wire.
Smart. Anything else for transverse?
Yes, a big one. If the lines change direction at a pole, like turning a corner that creates an additional sideways pull, a transverse load, that has to be factored in on top of the wind load.
Makes sense. The wires are pulling sideways at the corner.
And there are even special provisions under Rule 45.1. These acknowledge that sometimes, maybe because of property lines or obstacles, you can't place a guy wire perfectly to counteract these forces. So they allow for solutions like using side guys on adjacent poles, sometimes up to 800 feet away, to distribute that transverse load across multiple supports. Really clever engineering workarounds.
800 feet. Okay, that's flexible. What about vertical strength? Rule 46.
Vertical strength is mostly what you'd expect, supporting the weight of the lines, the ice load in heavy districts, transformers, other equipment. But it also includes this very specific test requirement. The structure, particularly crossarms, must be able to support a 300-pound load applied vertically at the end of one crossarm.
300 pounds? Is that like simulating a worker climbing on it?
It could be partly that, or just an extra measure of robustness for unexpected vertical loads. It's a standard test point.
Okay, and the last one, longitudinal, along the line.
Right. Rule 47, longitudinal strength. This deals with forces pulling along the length of the line. The main source is the tension in the wires themselves, the maximum working tension. Often, guy wires or braces are used specifically to handle these longitudinal forces, especially to prevent the pole from bending too much along the line direction.
And this must be really important where the grade of construction changes, or at the end of a line, right?
Absolutely critical.
Yeah.
Rule 47.2 covers change in grade of construction. If you're going from, say, a grade B section into a higher grade A section, the last support pole in the lower grade section and the first support in the higher grade section have to be strong enough longitudinally to handle an unbalanced load.
Unbalanced how?
Imagine all the wires pulling in one direction. That end support needs to withstand the total combined pull of all conductors and messengers pulling from that direction. There's a cap, usually 50,000 pounds, but the key is the safety factor required here is just unity, a factor of 1.
So strong enough to handle the absolute maximum pull, but with no extra margin, like a last line of defense.
Exactly. It's designed to contain a failure, to prevent it cascading down the line if something breaks.
And what about just regular ends of lines, like dead-end poles?
That's Rule 47.3, end supports in grades A or B. For lines that are grade A or B throughout, the end support structure needs to withstand the longitudinal pull of 1/3 of the total conductors. And importantly, you choose the specific 1/3 of conductors that would create the maximum possible stress on the support structure.
So you're designing for the worst-case scenario of which wires might fail or exert the most pull?
Precisely. It's all about identifying that potential weak point and making sure it isn't actually weak.
Okay, this is already incredibly detailed. We've got grades, loading, safety factors, directional strength. But I imagine the document gets even more specific, right? Down to the actual material.
Oh, absolutely. This is where it gets really granular.
Right.
Rule 48 dives into the strength of materials, how you actually determine the strength values to use in all those calculations.
So, like, how strong is wood versus steel versus concrete?
Exactly, and with very specific standards. For wood, Rule 48.1, they reference specific types like Douglas fir and assign designated fiber strengths like 8,000 pounds per square inch for Douglas fir. They cover natural round poles, sawn wood timbers, even laminated wood, often referencing specific ANSI standards. And remember that degradation idea. There's a note about long-time loading for sawn wood, where you actually have to multiply the allowable stress by 0.55 to account for strength loss over time under sustained load.
Wow, okay. What about steel?
Steel, Rule 48.2 design, follows specific engineering standards like from the ASCE, American Society of Civil Engineers. It involves formulas for tension, compression, shear, bending. And they define minimum yield strength and tensile strength values for the steel used. Very precise material specifications.
And concrete?
Concrete, Rule 48.3, has its own detailed requirements too. For reinforced concrete, they specified the minimum strength of the reinforcing steel and the compressive strength of the concrete itself, like 2,400 psi after 30 days of curing. Pre-stressed concrete has even higher strength requirements for both the steel tendons and the concrete. It shows the level of material science involved.
Okay, so the materials are specified. What about the components themselves, like the poles?
Right, Rule 49 gets into the details of poles, towers, and other structures, Rule 49.1. For wood poles, it starts simple. They must be of sound timber, basic quality control. But here's a fascinating concept. Rule 49.1a talks about poles with guy wires. It essentially says that the section of the pole below where the guy wire attaches is considered merely a strut.
Merely a strut.
Yeah, meaning the guy wire is assumed to take all the horizontal load. The pole below that point is just holding things up vertically, acting like a column under compression. The guy's doing the heavy lifting against the sideways forces.
That really highlights the importance of those guy wires.
It does. And then there are the physical dimensions. Rule 49.1b dimensions. This specifies the minimum top circumference for wood poles.
You mentioned this earlier, how fat the top needs to be.
Exactly. And it varies. A grade A pole in a heavy loading district needs a top circumference of at least 22 inches. But a grade C pole in a light loading rural area might only need 16 inches. It's tailored to the load and risk.
Incredible. What about how deep they go in the ground?
That's covered too. Rule 49.1c, setting depths. Table 6 gives minimum depths based on the pole's total length and whether it's set in soil or solid rock. For example, a standard 40-foot pole needs to be set 5.5 feet deep in soil, but only 3.5 feet deep in solid rock.
Makes sense. Rock provides more support.
Right, and there's even an allowance if the ground erodes a bit around the pole. You can go down to 90% of the specified depth, but no less. A bit of real-world wiggle room.
And gains. What are those?
Gains, Rule 49.1d, are the notches or flat surfaces cut into the pole where crossarms attach. The rules specify how these should be made, like slab gains or using metal bands, and even how deep the cut should be, typically 1/2 inch to 1 inch, to ensure a solid, stable connection for the crossarm.
Okay, speaking of crossarms, Rule 49.2.
Yep, crossarms. If they're metal, they need to be corrosion resistant. They always need bracing to stop them from tipping sideways. And remember that 300-pound vertical load test. That applies here, testing the crossarm strengths near the outer end.
Right, the 300-pound squirrel test.
Hey, yeah. And they also specify longitudinal strength for crossarms, how much pull they can take along the direction of the line before failing. It's typically around 700 pounds for supply line crossarms, 400 pounds for communication line crossarms, and interestingly designed with a safety factor of just 1 in this specific test.
Factor of 1 again? That seems to pop up for specific failure points.
It does. It's often about ensuring a predictable failure point or just meeting the absolute maximum expected force in a specific scenario. And they often require double crossarms, one on each side of the pole for extra strength when dealing with unbalanced longitudinal loads, like at corners or dead ends.
Okay, down to the final connection points. Pins, fasteners.
You got it. Rule 49.3, pins and conductor fastenings. This covers the insulator pins, the things that hold the insulators that hold the wires. Materials are specified. Galvanized steel, iron, even locust wood is permitted for pins. Minimum diameters are given 1.25 inches for wood pins, 1/2 inch for metal pins.
Locust wood. Okay, that's specific. What about the tie wires that hold the conductor to the insulator?
It's also covered. Tie wires need to be made of material that won't damage the conductor itself. Table 7 gives specific sizes materials, often annealed copper or galvanized steel, and the pins and ties together have strength requirements. They need to withstand a certain unbalanced pull from the conductor. For power lines, it's often 40% of the conductor's maximum working tension capped at 500 pounds. For communication lines, it's lower, maybe 15% of tension, capped at 300 pounds.
So even the tiny little tie wire has a specific strength calculation behind it.
Every single component does. It has to ensure the integrity of the whole system.
Wow, what an absolute incredible deep dive. We started just looking up at these poles, wondering how they stay up, and, well, now we know. It's this amazing, intricate symphony of physics, material science, risk assessment, safety factors, all meticulously documented in rules like these. From the big picture grades of construction down to, the type of wood used for an insulator pin or the setting depth in soil versus rock. It's just a testament to the hidden engineering all around us.
It really is. And all this incredible detail, all this complexity, it exists for one primary reason: to keep the lights on, the data flowing, and most importantly, to keep the public safe. It's work that's largely unseen, often unappreciated, until something disrupts that reliability and safety. And it really makes you wonder, doesn't it, what other complex, hidden systems like this are supporting our daily lives?
That's a great point. And maybe something for you, the listener, to think about next time you're out and about. Look at those lines again. Consider this. How do regulations like these manage to balance that absolute need for safety, that incredible level of detail, with the real-world pressures of cost, maintenance, and trying to innovate with new technologies? What does this kind of foresight, this meticulous planning for public infrastructure, tell us about how we manage other critical services we rely on every day? Definitely something to mull over.